Hi folks, this video tutorial is about the natural frequency calculation of a composite laminated composite plate which is simply supported on all edges. Uh, this can also be titled as free vibration of a laminate, because once you have the natural frequencies, obviously the free vibration is set. Now, the reason I'm using this particular geometry is that I want to be able to compare my CATIA's native FEA solver calculations against something that I have analytical solution. And this particular problem does in fact, is a simple one, does in fact have an analytical solution. And I'm going to be talking about that in a minute. First of all, the geometry. This laminate composite is made of 3 layers, 0, 90, 0, and they're made of the same material. Therefore, this can be viewed as a symmetric laminate. And because the angles are 0 and 90, it's called a cross-ply laminate. Okay, the thickness of each laminate is 1 millimeter, and a couple of comments about this particular setup. Because it's a symmetric laminate, we have the matrix B. Those of you who know a little bit about the ABD matrices and elementary composite laminate theory, matrix B is 0. And because it's cross-ply, we have some of the cross coefficients 0. A16, A26, and B16 and B26 are 0. Okay. And one other comment is that when I do this in CATIA, I'm going to do only 2 plies, and then I'm going to tell the software that it is actually symmetric laminate and it's pivoted. That means that don't do 0, 90, 90, 0. Do 0, 90, 0. That means it's pivoted. It's not a big issue because there's only three plies here. I could have done all 3 of them one by one. But just to remind you how symmetry can be used to minimize your work in CATIA composite design, I'll do 2 of them, and I say then symmetric and it's pivoted. That means don't do 4, just do 3 according to the setup. Now, the geometry is taken to be square, as I said, 0.5, 0.5, but we don't gain anything by doing 0.5, 0.5. We're making a square. It can be a rectangle, and the problem is analytically done for rectangular plates. In that case, there's an aspect ratio parameter that pops up in the theoretical formula that for us is 1. Otherwise, it's whatever the ratio A over B is. And the way I do it is that I'm assuming, although it doesn't matter, I just want to remind you the way I'm going to set it up is the 2, 0, the 90 degree, the 90 degree ply is along the y direction. The fibers go in the y direction, and the 0 ones, the 0 degree plies, uh, the fibers go along the x direction. Okay, this has some implication when it comes to viewing the frequency mode, natural frequency mode. Okay, simply supported on all 4 edges simply means that displacements are all 0. Nothing about rotation. Rotations are left alone, and yeah, and therefore the moments are going to be 0. Moment about those axes are going to be 0. That's what simply supported means. Now, the other comment that I have to make is uh, in composite problem, try not to use symmetry, finite element symmetry, because if you're not absolutely sure that this is going to be this mode is going to be symmetric mode, or the calculation allows you to take only 1/4 of that, 1/4 of this geometry, try not to use it, because sometimes it's obvious, sometimes it's very difficult to see. So I use the entire model. The material properties that I'm going to use are taken out of Jones's textbook, okay? And it's high strength carbon epoxy. So the four numbers that you need here, E1, E2, U12, and G12 are given there. And the density of this is also given here, except that be very careful, because this density is actually weight density. It says Newton per meter cube. So you divide it by G, the gravity constant, 9.8, and the number that you put in CATIA, it has to be mass density. Therefore, it's going to be this divided by roughly 9.8, and it's going to be almost 1. Okay, now, so here's the situation. First of all, this is a CATIA dialog box for the composites. Notice that I'm defining the thickness of each, the acute thickness of each ply to be 1 millimeter or 0.001 meter unidirectional. And this is the information that I input from that table, except for the density. See the density here? I divided it already by 9.8, so I put 0.98, etc. Now, uh, these numbers, this is for a strength calculation, which we don't consider in this problem, but if we did have to use a strength in a static problem, you put them in these rows. I've talked about this thing in the earlier videos, I don't know, 3 through 4, something like that. Now, this formula comes from Jones, although it's not due to him. Many people have this thing. It's a standard problem, standard type of problem. People have it in many textbooks. But so notice that if you're going to use this theoretical result, okay, uh, yeah, so then D11, D12, D66, and D22 are needed. Okay, so somehow based on your laminate configuration, maybe your own spreadsheet, whatever, you need to calculate these D's, okay, and plug it in to get the theoretical value. Let me go to the next page. So when you look at the results later on, I'm going to do that in a few minutes. When you look at the results anymore, they look like this. So notice that this is the first mode. Katia gives you 2200, almost 2200 hertz. This is the second mode. Now notice that because it's stiffer, the two 0 degree plies run in the x direction. It's stiffer in the x direction, and therefore you can see that the vibration tells you that that there's going to be two half waves along y, and this is the third one, third frequency, again 3 half waves along y, and finally it's going to go here and it gives you two half waves along x. Okay, the other thing is that the formula that I wrote for you, I'm repeating it here, except that I've divided the square, taken the square root of both sides from that formula that I showed you, and then I've divided it by 2 pi to get this thing in hertz. So this is in hertz, okay, and the calculation done by the formula that I just showed you, this formula above, are these numbers, and when you compare it to what CATIA gives you, it's almost 1% error. There's one word of caution here, but these are the values that I use for getting the theoretical calculation. These don't come out of CATIA, because CATIA program will not give you the D matrix. Some other packages do, but not CATIA. Just a word of caution here, this row not here, this is not the density. This is the density times the total thickness of the laminate. So I have three 1 millimeter plies or laminas, and therefore 3 times 0.01. So what the number that goes in there, if you're going to use this formula, is going to be the actual density, mass density, times the height of the laminate. Okay, don't worry about that, because we're using CATIA. We don't have to worry about these in CATIA. We just have to make sure that the proper rho, which is mass density, is inputted. These calculations are done in release 2018 of the CATIA V5-6, and if you're using other releases, there may be some minor differences in the uh, interfaces, in interface dialog boxes and icons. Very few, very few. Okay. Okay, so let's go ahead and get down to business. So let me calculate. Let me first of all make my geometry very simple. So let's start the file. We're going to do a part, and I'm going to put that thing in the folder. In a folder, I forgot to change the color of the background. Options. Okay, so display, visualization, not white, standard color. Okay, and then immediately I'm going to save this thing. File, save management, save as. I made a folder called frequencies, desktop frequencies right there, and part one, very good. So it's going to go in there. All it is a square, half a meter by half a meter. So on that plane, I'm going to sketch, a square like that, dimension it. This is half a meter, 0.5, and this is half a meter, 0.5. We're going to fit it, exit, put a surface through this. Right there, I use a fill, or is that the fill option right there? And it, for that sketch, put a surface through that sketch. It did it, and I always join it because I want to have a control over the direction of the surface, which in this case, you can if you double click on join, it shows you it's upward. I flip it by selecting it, and now if I look at the direction, it's downward. And the reason I do this thing is that when a shell mesh is put on this surface, it has a normal to the shell element, and the way CATIA is written, the direction of that normal is always opposite to the direction of this join. Okay, so we saved everything. Now we're going to have to create our material. Now this is not something that's available in CATIA database, so I have to type these things in, and I'm going to do that. So file, start, uh, infrastructure, material library. It just creates something for me, so I double click on this thing. This is blank now, so the name of it, I'm going to call my carbon epoxy. How about that? Carbon epoxy for vibration problem. Okay. Apply. Notice that the name of this thing changes. Now we're going to go to composites. The thickness I already put down a millimeter here, 0.001 meter. Okay, but it is unidirectional. Apply, and then analysis tab. We want a 2D orthotropic, and all those numbers that I gave you from the table, Jones's table. So the first one is 128 GPA, 128. I think it was 128, right? 128 GPA. So instead of writing 128 e to the 9 Pascal, I can just type GPA. It's going to convert it to Pascal for me. The next one is this is a transverse direction, uh, 11 GPA, 11 big G, big PA. Okay, that's going to convert it to Pascal because that's what my units are in. Poisson ratio is 0.25. Shear modulus in the direction 1, 2 is 4.5 GPA, 4.5 big G, big P, big A. Now these other ones, these are the transfers, these are shear modulus in other directions. We don't use it for classical lamination theory that CATIA is using, but I always, because I don't want to leave zero here, I always put half of that. I don't know whether zero is going to complain or not. You may want to try one day to put a zero here to see what happens, but I'm going to put half of this one. So it's going to be 2.25 big G, big P, big A, and 2.25 big G, big P, big A. Now I can tell you that CATIA uses these things, but for the purpose that we have in mind, these are not needed because those formulas that I gave you from Jones's book assumes classical lamination theory. In other words, shear stress along the thickness is zero, okay? Or shear stress along the thickness is zero, which means shear strain along the thickness is zero. But it uh, you know, CATIA does not make that assumption, but because of the nature of the problem, those shear stresses are probably so small that it's going to be assumed to be zero. Okay, so here, density, what did I do? I remember I divided whatever Jones gave me, and I divided it by 9.8, and it came out to be 0.98, 0.98, okay? Right, that's it. So this is good. I think we inputted anything that we wanted. I always check these because I tell you it has happened to me that I think I inputted the right stuff and I did it, but then somehow internally this goes back to isotropic, and then when I run it, it can't find the material. Anyway, I always check this thing. Okay, now save it. I'm going to put in the same folder, frequencies, not here. I call it frequencies of square plate Jones. Yep, that's it. I can change this name, so I'll call it frequencies. How about that? Just so that I can recognize the database, the material database that I'm creating, just so I can recognize it. Frequency square plate joints, yeah, that's what it was. And then, okay, now I'm gonna save this. I think I already saved it, right? Yep. So I'm gonna close that. Okay, so we are ready to create our laminates. So we go to composite design. Okay, parameters, composite parameters, add the material. We're going to go to that database that I created. It was desktop, right? Desktop, and it was frequencies, square plate. This is the one that I created. Remember, I renamed it to frequencies so that I could easily find it. Good. Okay, so we added the material and directions, standard 0 and 90. We don't have to add anything. Rosette, we don't have it, so we can add it. And notice that by default, which is going to try to create it at that location, but I'm going to create one. It puts it there, which is fine. There's nothing wrong with it because but I always like to move this thing a little bit away so that I can see what's going on. So let me see now. Yeah, right here. So create a point, and for the point, I go maybe I don't know, maybe minus 30 millimeters. Oops. Let me cancel that. Cancel that. Okay. So create a point. The y direction is minus 30 or minus 30 mm, 300 mm, so I can see it right there. Okay. 30 mm is too close here. I didn't even see the motion. Okay, so make sure that this is not current. Let me say, all right, so there is my rosette, and we're good. So we created the rosette, and this dialog box can be closed. Okay. Now, if you don't like to see your rosette, you can always, hide it, or this is fine. Okay. The next thing is I'm going to create my ply group right there. So I'm going to do it manually, ply group. So the surface right here, the dripping direction is up. I was like up, and this is fine. Lock the direction of the plies. Okay, good. So now we're going to create our plies. So the first one is going to be 0 in that group. And for the boundary, I'm going to select that sketch right there. You can see that. And obviously the first one is going to be 0. And this is the material that I created, right? So we say, okay. Then I'm going to do the next one. This was the first ply. You can see that. This was the first ply. The next one, same group. And the boundary is, again, that surface, not surface, that sketch, either from here, or you can even take this boundary here. It takes the previous boundary. It really doesn't matter, okay? And the direction is 90. Good. Now, if you want to see whether you have done it right or not, you can always use the ply exploder to make sure it is what you wanted. So notice that there's 0 and 90, cancel. So what I want to do now is I want to create a symmetric configuration. So you go and find this icon here in the plies toolbar. There's this thing called symmetric. It says what is the group that you want to use. Well, it's this group. And you want it to use pivoted or non-pivoted. Pivoted means, non-pivoted means that take 0 and 90 that I just created and reflect that, so there's going to be another 90 and another 0. Pivoted means don't worry about the 90. Take the 0, 90, and reflect to get the 0. That's what I want, right? Pivoted. And we can always check. If I had done the non-pivoted one, it would have been 4 of them, obviously. If you look at this, there should be 0, 90, 0. Right, 0, 90, 0. Very good. Cancel that. We don't need it. Save everything. Now we are ready to go to the uh, finite element module. First, we're going to go to advanced meshing tools. Now, you don't have to go there. You can go directly to generative structure analysis, but the only option that you have there for the type of element is triangular one, 3-noded triangular one, or 6-noded triangular one. But I want to do a nice rectangular type of mesh, so I have to go to advanced meshing tool. I have no other choice. Okay. Now, look, uh, notice that here, this is very important. Because here it gives you the option of getting into static or getting into dynamic, okay, frequency. I want to go into frequency, but on purpose, I will not choose this, okay? I will, on purpose, I pretend that I was careless and I didn't read this thing and I just went ahead and, did it like this. Okay, fine. This was on purpose. I could have stepped. I can skip one step later on if I just select dynamic or frequency from here. Okay, so where is the mesh? This is the mesh. Okay, the size I'm gonna make. Let me see now. Yeah, I had 50 or half a meter on each side, and I want to put 20 elements there. So, but it just happens that this is correct because I already used it. Okay, so that's going to be 20 elements this way, 20 elements that way, and quadratic, parabolic, fine, and then mesh it, and then OK, and exit. So this is done. So we go to generative structure analysis. Notice that it didn't ask me whether the step was static or dynamic because in the previous earlier I told it was static. This is why I created static for me, and I don't want this thing, but just be patient for a second. Let me save this thing. File, save management. There is the analysis, save as, in that same folder, analysis one. Okay, very good. Okay, let me also put my restraint, and then I'll tell you what we need to do about the static case. So first thing I do, I hide the plies. There it is. This is stacking. Hide this. It takes away some of these things on the edge, and I hide the sketch. Now I can access every single edge by itself. Okay, good. So why don't we look at the mesh first of all? So put the cursor on nodes and elements, right click mesh visualization, and change the rendering so that you can see all the 20 elements. Okay, fine. Now we're going to hide this because when this is showing on the screen, there's nothing you can do. Nothing else you can do. Okay, so let's apply the restraints on the edges. So it's going to be user defined. These 3 edges, all of them are prevented from moving in any direction. Now, notice that this is different from clamp, because if you clamp this, that for shell elements, rotations are also degrees of freedom. It's also going to assume that the rotations are 0, and that is not the same problem. That's not simply supported. Very good. Now, that's pretty much it. That's the only restraint that we have here. The only problem is that this is a static problem. I asked for a static problem. If I ask for a static problem, obviously I have to put a load on it, and I don't want to do that. So what I do, I realize that, oops, this was not meant to be. So I go here, I say insert frequency case. Insert frequency case. And then it says, okay, you want to insert a frequency case? I have no problem. But tell me which one, or if any, of the restraints that you already put on the static one you want to use. And I'm going to say, yes, I want to use the stuff the restraint that I defined on the static case. And then it says, go pick it. So obviously, this is the only thing that I did. This is the only restraint that I pick it. So for the dynamic one or the frequency one that's going to be created is going to be using exactly the same restraint. I forgot to say, initially, I forgot to say, I don't want a static analysis, I want frequency, I forgot. But then when you do that, you come back and say, insert whatever you want. And of course, it asks you, are there any restraints that you want to carry with you from here, or you want to do that independently in the frequency case? This is it. So let me save it and run it. Nothing else to do. Oh, you know what? I forgot to tell what my composite properties are. That's what this thing means. It says acquisition feed failed, could not find any property. Good, because I forgot. So right there, you go there. There is the imported composite property. You click on it, and it's going to be by ply. First of all, support is that surface by ply. And now I have to go and select my ply, which needs to go here, ply group, right there. And symmetric. What symmetric means, that be careful, this symmetry, that's a different meaning that the symmetrical layout, layup, or this means that, okay, you told me that you have 3 layers, right? Would you like me to put 3 layers or these 3 plies so that this plane is exactly halfway between it? And the answer is yes. If you say, no, I don't want that, I want to stack up those things on top of this in one direction, you have to obviously remove that. Now, in some problem, that really doesn't matter. And I have a feeling that even in this problem, it really doesn't matter. But I want to do it exactly the way I described it. So I have 090 made on this thing. In other words, half of it up, half of it done. Therefore, I say symmetric. You may want to try it without symmetric. I have a feeling that you're going to be identical. As a matter of fact, we're going to come back and try it. Okay. So symmetry, and now we're going to run it. Done. So let's look at the mode, displacement mode. Double click on it, change average ISO, and change the rendering here. Change the rendering to material shading. Okay, so double click on it so that you can get all the modes. So that was the first one, 22168, and I believe that this is what I had here. 22168. The next one is 37, etc. Yeah. So these are the things that I showed you. Now, I'm going to try it. I'm going to go back here to this property that I used here. Double click on it, and I'm going to change this to non-symmetric. I have a feeling that these are, in this particular problem, it's not going to make any difference. We'll see. Okay, so let's go ahead here. Where was it? This is the one that I created. Right click, activate, and oh, it does. It does. Yes, yes. It does, because just think about it. Yes. Uh, when it says symmetric, it means that okay. So let me go back to here. When it says symmetric, that means that we are assuming that the plane, the simple support, is right in the middle, in the middle of this layer. Okay. Now it is not hard to see. In other words, the points right in the middle of this, the stack is not going to move up or down or sideways. Simple support. But when you put at the bottom, just think about it from dynamic point of view, there is more mass on one side of this support area. So I was not quite sure, but now that I think about it, it makes sense that these numbers are different. Okay, so yeah, basically here what it says is that it became stiffer. Remember the first mode? The first mode in the other case was 2200. This is 3000 first mode. That means it's stiffer for vibration in that direction. Okay, and uh, you got to be careful. You got to be careful. Some of these are not obvious. All right, folks, have fun.